Hello. Today, I want to talk about parametric equations. So the idea here is that we can describe things that we wouldn't have as functions, and we can describe them as functions. That's kind of one really nice way to do this. Another thing that we kind of motivate this topic with is the idea of motion in a plane. So in particular, in calculus, in Calc 1, and in earlier in this semester, we talked about velocity versus the position versus the acceleration. And so you remember we sort of have this idea that, if I have the velocity function, I can get the position function by integrating that. And that position function, we didn't really emphasize, is a linear position. So in particular, when I tell you this function s of t is the position function, and it's something that involves t, I'm talking about the motion of an object along a straight line path. So I'm not talking about the motion of an object through two-dimensional space, not even at all three-dimensional space, just in one-dimensional space. So is it going forwards or backwards? And how fast is it going forwards and backwards is the velocity of that position. And then acceleration is sort of how fast is that velocity changing, right? So here we've only really discussed the position of an object moving in one-dimensional space. So what I would maybe mention here is, well, okay, that's great and all, but how am I going to describe what happens in two dimensions? So if I want my object to be, say, moving around a circle centered at the origin, well, I have to tell you the position on that circle. And so to tell you the position on that circle, I don't just need x equals something or position equals 4. What I need position is this point in the xy plane. It's x value and y value. So I need to give you two values that give you the position of this moving object as it moves around the circle. So what are we going to do? So in the sort of Calc 1 sense, I only know the straight line path. So to talk about a more complicated path, I suppose, I need to think about, how do I describe position in 2 dimensions, or in 3 dimensions, or in 4 dimensions, or in 5 dimensions, or as many dimensions as I want. I want to be able to describe the position in that dimension. So in our case, 2 and 3 is the kind of ultimate what we need to do it with. I want to talk about 2 to start with. So I'm going to make this easy. We're going to talk about an object moving around a circle centered at the origin. Radius is 1. That'll sort of give us an easy calculation for all of this. And I'm also going to make it easy. Doesn't seem easy, but I'm going to make it easy by saying that every 2 pi hours, this object goes once around the circle. So you're sort of thinking I'm on a racetrack possibly, and I'm driving my car. And as I drive the car, I'm certainly not racing on it. Every 2 pi hours, like 600 hours, I make 1 full revolution around that racetrack. Okay. So how are we going to describe the position of that object at any given time? So you can kind of see why that 2 pi is going to be important. So 2 pi, 1 full revolution happens in 2 pi hours. So in pi hours, I've made half a revolution. In pi over 2 hours, I've made a quarter of a revolution, and so on. So you can sort of see that, in fact, the angle here that is made with the axis, the theta here, is going to be the position. It's going to be how long, how much time has elapsed in hours. So theta hours, after theta hours, I'm at this point in my xy plane. And notice this is a circle of radius 1. So this is the unit circle. And the points on the unit circle are described by cosine of the angle formed with the x-axis and sine of the angle formed with the x-axis. And so you can sort of say, hey, look at that. In this object, I can actually tell you exactly the position after theta hours by plugging theta into cosine theta sine theta. Okay. So what we do is we say, oh, that's awesome. What we're going to do is really talk about it as 2 functions. there's an X function and there's a Y function. Both of those functions depend on time, the T. The X function is going to, X position is going to be given by cosine of T. The Y position is going to be given by sine of T. So this is giving me an X and a Y at time T after T hours have elapsed. Okay. So this is giving me my position. And so you can sort of think, well, hey, you know, I could probably find like a velocity, but unfortunately, the velocity that I find, it has to be kind of split. I've got a velocity in the X and I've got a velocity in the Y, and those two velocities are not the same. And so we need to think a bit about that. That comes up again in Calc 3. How do we describe then the velocity along the path that we're taking? So you're sort of thinking about this circle, the velocity along the path, the direction I'm going is essentially along the tangent line. So you can think that the direction that I go as I traverse this circle is following the tangent line. So at any given point, the tangent line tells me that's the direction that I want my velocity to be pointed. And so to find the velocity, I'll need more information than just what's the velocity in terms of X and what's the velocity in terms of Y. And so here we can't quite do the velocity yet, but this is a good setup to start into where do we get the velocity. And that comes up in Calc 3, like I see. Okay. So this is nice. So we sort of have a way of describing a position in 2 dimensions after a certain amount of elapsed time. So in general, what we will do is we call this T a parameter. I have an X function and a Y function. Though X is a function of the parameter, Y is a function of the parameter. Okay. And so as the parameter runs, the X and the Y change. And so you can sort of say, okay, so I could make some sort of strange function that has X is something and Y is something else. And what does that graph out? What is that going to look like? What are we going to have as the curve? The big advantage that we get from this is that I have X and Y are both functions. And I can get strange things coming out of this that are not functions if I treat Y as a function of X or X as a function of Y. But they are functions when I treat them separately as f of t and g of t. So those two things are functions, but when I try to cram them back together, I don't get a function out of it. All right. Speaking of which, that's kind of what I want to do next, is to think, how do I figure out what the curve is that I'm trying to map out? So I'm going to give you sort of a parametric equation here, that x equals negative 2t, y equals 5t plus 6. How do I figure out what is this mapping out? Well, it turns out I can solve for the t in one of my 2 equations. And in this case, I'm going to solve for t in the first equation. That's the easiest to do. I get t is negative x over 2. I plug that t into the first equation and replace t with it. And that's going to give me a y is some function of x. So y is negative 5 halves x plus 6. So this parametric equation here is describing a line, slope of negative 5 halves, y-intercept of 6. So the question is, why don't we just do it this way? Well, we've lost some information. In particular, one of the big things we've lost is how am I traversing this line? So I'm going along this line. I'm going, down or up this line. How am I traversing this line? So what does it look like? How am I mapping it out? So what I do to figure that out is I will plug in some t values. So when t is 0, I get 0, 6. So 0, 6 is the point when I have t equals 0. When t is 1, x is negative 2, y is 11. So 5 times 1 plus 6 is 11. Okay. I can keep going, but I know this is a line, so it's sort of pointless to keep going, but I'll do it. X is negative 4 when t is 2, and y is 2, 10, 16. So what I am doing as I graph this line out is I have 0, 6 as my first point. Then I have negative 2, 11 as my second point, and then negative 4, 16 is my third point. I'm mapping this thing out from bottom right to upper left. So I'm going that direction on my line. So not only does this parametric equation give me a curve, but it actually gives me like an orientation of a direction of the curve. And so what I would call this is I would call this a positive orientation, is the direction that this curve is being mapped out by the parametric equation. So this is the positive orientation of this curve given by x equals -2t, y equals 5t plus 6. So this is positive orientation. So we have this positive orientation along that line going from the lower right to the upper left. Okay, this will become sort of more important as we start thinking a little bit more about curves like this. So in particular, talking about an arc length, the arc length has to be mapped out in the direction that I'm going. So I'm not sort of going forwards, I'm going backwards. It's kind of a what is forwards, what's backwards when I'm doing mapping this thing out. That's the important part. Okay. So it's also possible that I could maybe not find a function just with y equals something in terms of x. In that situation, my math lab, some of the problems will have you do something like, well, y is equal to the plus or minus the square root of x plus something. I say 4, why not? And that's fine. But notice I could actually do this a different way. And that is to treat x as a function of y. So I could do this. This is actually one of those examples where my math lab wants the square root of x plus or minus square root of x for this one. But personally, I would solve for y. Solve for t in terms of y. So I solve for t in this second equation. T is y minus 9. Then I plug that t into the first equation. It gives me y minus 9 plus 5 quantity squared. Evaluate that, I get y minus 4 squared. And then we need to think about what this is. This is a sideways parabola. It's a vertex is 0, 4, and it opens to the right. So it looks like opening right, kind of like a Pac-Man going to the right. And so you've got this sort of shape going here. How is it being mapped out? That's another question. So when t is 0, what do I get? So when t is 0, x is 25 and y is 9. When t is 1, x is 26 and y is 10. Okay, so it appears what's happening here is that I'm at 0, 25, which is here, and then I'm actually kind of opening to the right. I'm going that direction, and I think I have to be careful. So at 0, 25, I'm actually here and then I'm going this direction, right? All right. So when t is 0, I'm at x equals 25, y equals 9. T is 1, I get 26, 10. So I'm this positive orientation along this curve is from the bottom to the left, up past the vertex and over. So you're actually going kind of this direction on the curve. That's the positive orientation. Okay. So by eliminating that t, we actually lose that information about which direction does it go, so that the direction that it maps out with the t values as t increases, that's called the positive orientation of the curve. You can reorient the curve so that it goes the other direction. And so just have to think a little bit about how to do that, but you can actually make this thing, instead of mapping out that parabola in the positive direction we showed before, can I maybe reorient this thing so that it maps it out the other way? You can think about how you might do that. It's not too hard to do. I won't do it for you. I'll let you think about it. Okay. We can also use our graphing calculators to graph parametric equations. So we can switch the mode to the parametric mode. So you go to parametric mode, and then you go and you graph these things using t as the variable. And so when you go to parametric mode, what comes up is you get two equations, an x of t and a y of t. And so you just plug in an x of t, you plug in a y of t, that gives you what you need. If you're not using a calculator and you want to use a computer, you can do that as well. So you can get a Wolfram Alpha or to whatever your favorite one is. For Wolfram Alpha, you need to do parametric plot. Okay, so you do parametric plot, and then you enter the curves that you want. So it's going to be, the first one will be x, the second one will be y. Okay. So let me give you an example. So in our slides here, our example is t cosine t and y is t sine t, where t is greater than 0. So what does this look like when I graph this out? So I want t cosine of t, comma t sine of t. So this is giving me the x and the y, and I want t bigger than 0. So I'm going to say t from 0 to 10. Why not? We'll just go from 0 to 10. And just see what happens. So you can see here what's going to happen. Maybe I haven't gone quite far enough. I, in fact, haven't. But it's a spiral, basically. So what you get from this is you get this sort of shape mapping out from 0 onward of a spiral. Spiraling from the origin out around counterclockwise. So it runs counterclockwise as t goes greater. So let me try one more. I'm actually going to give you some more values here. So instead of 0 to 10, that was 0 to 100. So you can sort of see exactly what's going on here. On your graphing calculator, you may need to change the window. So the window will tell you a couple of things. So that it'll tell you a t min and a t max. That's how small and big t can be. So for this one, you would go t equals 0 is the minimum, t equals 100 is the maximum. And then it gives you also an x and a y value for the plot. So here you would go for like x is negative 100 to 100, y is negative 100 to 100, and you'll get this plot that looks like this from 0 to 100. And then t-step, the t-step inside of your window there tells you how often it should calculate. So if you take a t-step that's too high, you'll get a really blocky kind of shape that's not mapping it out correctly. So take t to be smaller. So take t to be like 0.1. And the point of this is if you take t too small, it's going to take forever to graph. If you take t too big, it's not going to look right. You're going to get this kind of blocky, connect the dots kind of thing. All right. So this is pretty cool. You can play around with this a lot. So, you can say, well, what happens if I put a 4 inside there with the t in the cosine? And just see what happens. And hey, look at that. That's kind of cool, right? So you get this kind of strange looking shape here. It's kind of fun. And you can do a lot with this. You can play around with it more. What if I then change the sine to a 4 as well? I think if I change the sine to a 4 as well, yeah, I get back to this spiral with a lot more going on because the sine is running faster around the from 0 to 1, negative 1 to 1, sorry. And so you're sort of running this thing around faster and faster and faster. So sort of spirals. All right. So you can play around with it, and I suggest playing around with it a little bit to sort of get a feel of what all these things do when you change the t, when you change all the shapes and all that kind of stuff. Cool. The other thing I would point out, though, is that this is certainly not a function. There is no way this is a function. Like I certainly do not have a function here, but it is a function of both x of t and y of t. So the two x and y values are a function of t. The ultimate function that I get, the graph that I get, does not have y as a function of x. It does not pass the vertical line test. So it certainly does not pass the vertical line test. There's a whole lot of these things cutting through that vertical line, any vertical line I draw. Okay. Cool. So what's the benefit then? So the benefit to us is that if we give you something in parametric mode, I can treat it like a function. So I can ask for things like, what's the slope of the tangent line to the curve at a given t value? And for that given t value, it's going to be uniquely nicely determined. So that I can differentiate the function because these are nice differentiable functions. They're not strange, weird functions like a circle or in this case, a spiral. When you have spiral given as y equals something in terms of x, that's not nice. You don't get something nice like this. So that's awesome. So I can find this. I can find things like the derivative. So the slope of the line tangent to the curve mapped out by that parameterized curve is just dy dt divided by dx dt. So I differentiate the y function with respect to t, divide by differentiating the x function with respect to t. And what I get will be something in terms of t, but what it ultimately means is it's the slope of the line tangent as a y equals mx plus b kind of thing. So this is m tan, I believe is what we call this in the book. It's the tangent curve slope. It is the slope, and that is in the tangent line y equals m tan x plus b. So there is a curve, a tangent line that has that slope, and I can give the equation of that line as an equation of a line. So we sort of get a nice, good equation of that line. Okay, so for example, what's the slope of the line tangent to the curve? What x equals 3t, y equals t cubed. And we could maybe even do this at a specific point if we want, but for now, we're just going to find the slope of the line tangent. So what I should do is I should look for dy dx, which is just dy dt over dx dt. And dy dt is 3t squared. That's an easy derivative for me to do. Dx dt is just 3. So the derivative of this thing is just t squared. So for example, I can even find not even the slope, but the equation of the line tangent to the curve at a certain point. So equation of the line tangent to the curve at time t equals 2 is just going to be 2 squared is just 4. And so that's the slope. And then the x value at 2 is 6. The y value at 2 is 8. So we're going to take y minus 8 equals 4 times x minus 6. And that's going to give me y equals 4x minus 24 plus 8. Or y equals 4x minus 16. Okay, so that is apparently the equation of the line tangent to this curve at the point t equals 2. Okay. And this is not a difficult thing to sort of run through, especially with these nice curves. You get good derivatives out of these things. It's pretty good. Finally, sort of the last couple things here, the arc length of a curve in a parametric form. So you have a parametric equation. The arc length, you're running in a positive orientation from A to B, or I guess if you could do it negative orientation, and it would just make this integral negative because you're going from the sort of flip the A and the B. You would look for the arc length of this thing as you travel along the arc from A to B in the time. So that arc length is going to be the integral of the square root of f prime of t squared plus g prime of t squared dt. You can sort of think about this a little bit in the other form of this thing. I have 1 plus dy dx squared. But in our case, dy dx is just g prime over f prime. So it makes sense that you can kind of separate the f prime and the g prime in your sum when you do this integral. It's kind of cool. So you can actually separate those two and not have to do this dy dx thing to figure out the arc length. So let's do an example. So an arc length between 0 and pi over 4 of this curve 4 cosine t 4 plus 4 sine t. And so I'm going to integrate from 0 to pi over 4 the square root of f prime of t squared plus g prime of t squared dt. So what do I get? I get the integral from 0 to pi over 4. Derivative of 4 cosine t is negative 4 sine t squared plus derivative of 4 sine t is 4 cosine t squared dt. This gives me 16 sine squared plus 16 cosine squared. The 16 factors out. Sine squared plus cosine squared is 1. And then I'll be happy. So I end up with 16 cosine squared plus sine squared. Cosine squared plus sine squared is 1. So I just get square root of 16, which is just 4. The integral of 4 is 4t. Evaluated between 0 and pi over 4. At 0, it's 0. At pi over 4, it's pi. So the arc length of this curve between 0 and pi over 4, for time, from time 0 to time pi over 4, I've traveled pi, a length of pi around that curve. So the arc length of this, the length of this curve is just pi. All right. Awesome. So you can do a lot of things with this. This arc length stuff is pretty nice. You can think about orientation a little bit. If I was to go backwards on this curve, the orientation would go backwards and this arc length would actually sort of not change. It doesn't change because when I do the derivatives, it sort of just takes things, it would go negative, right? Because the two limits of integration would flop. So you would have 0 and pi over 4 going to pi over 4 and 0. So when you flip those limits of integration, it switches the sign of your integral there. So you have an orientation. So you have positive arc length and negative arc length depending on the direction you're traveling on the arc. Pretty cool. All right. And so, like I said, you can also do things like the sort of directional derivative or directional velocity of this thing based on the velocity in terms of x and the velocity in terms of y as time progresses. And so we will do that in Calc 3. We don't do that in this one. Here we just stick with arc length examples. Okay. So next time we're going to talk about polar coordinates. So join me for that one.